Hi, welcome back. I'm Professor Ronald Vincent Santiago, and today we'll be discussing Module 13. Module 13 is about Case 1, faults in an unloaded generator, line-to-line fault. What is a line-to-line fault? The second most common fault is line-to-line, which occurs when two of the conductors come in contact with each other. With our laws of generality, we'll assume phases B and C to be the faulted lines. So in this diagram, we have a three-line system wherein line B and line C are in contact. So thus, the current relationship, the current during this fault condition, IA is equal to 0, IB is equal to negative IC, IF now is equal to 0. For the voltage relationship, we can say that since phases B and C are at a fault, the voltage VBG is equal to VCG. Phase B to ground and are equal. Phase B and phase C. Now, using the current relationships, we can get now the sequence fault currents to be equal to 1/3 multiplied by the inverse of matrix A multiplied by the phase current flowing to the faulted point. Now, since IF 0 is equal to 0, the negative sequence current at the fault is equal to 0, the positive sequence current at the fault is equal to 1/3 multiplied by the IB at the faulted point multiplied by the quantity A minus A squared. Whereas for the negative sequence, the fault is equal to 1/3 multiplied by the current IB at the faulted condition multiplied by A squared minus A. Now hence, we can say that the current, the fault current, positive sequence and the negative sequence are both equal but in the opposite direction. IF positive sequence is equal to negative of the negative fault current, negative sequence of the fault current. Now, using the voltage relationships, we can now get for voltage, the sequence voltages will just be equal to the 1/3 multiplied by the inverse of the matrix A multiplied by the phase voltages of the at a fault. Now, since BF for the positive sequence is equal to 1/3 multiplied by the quantity BAG multiplied by, or plus rather, A plus A squared times BBG, BF minus, or the negative sequence, is equal to 1/3 multiplied by the quantity BAG plus the quantity A squared plus A multiplied by BG. Thus, it will give us the relationship between the positive sequence and the negative sequence voltage at a fault condition. So, BF of the positive sequence is equal to the negative sequence of the voltage at the fault. Now, to satisfy the positive sequence of the fault current and the negative sequence of the fault current and the voltages, the positive sequence voltages and the negative sequence voltages, the positive and negative sequence networks must be connected in parallel. So, we already knew the positive sequence or the Thevenin equivalent of the positive sequence network and the negative sequence network, and based on this relationship for line-to-line fault, we can say that these two Thevenin equivalent sequence networks, positive and negative sequence networks, are to be connected in parallel as shown in the diagram. Solving the network for the currents, we now get the positive sequence fault current is equal to 1.05 angle 0 degree over J 0.1389 plus J 0.1456, and that gives us 3.691 angle of negative 90 degrees. Now, solving for the phase currents of this fault current, that gives us the A matrix multiplied by the sequence current, this fault current. So that gives us IA to be equal to 0, IB equal to negative 6.39, IC equal to 6.39. So these are the phase currents at a fault, the phase fault currents. Now, solving the network for the voltages, we now get the positive sequence voltage, fault voltage, that is 1.05 angle 0 degree minus J 0.1389 multiplied by 3.691 angle negative 90 degrees. So that gives us 0.537 angle 0 degree. For the negative sequence fault voltage, so that gives us negative J 0.1452 multiplied by 3.691 angle of 90 degrees, and that gives us a magnitude of 0.537 angle of 0 degree. So thus, we can now get the phase voltages of this fault voltage BA, BB, and BC to be equal to the A matrix multiplied by the sequence voltages of the fault voltage. So that gives us BA to be 1.074, BB to be equal to negative 0.537, and BC to be equal to negative 0.537. So that ends our module 13. See you in our next module.